Now, I'd like to talk just a little bit about the effect of Bardhabunga on recent temperatures.
Here on the y-axis
Is the average temperature per month reported by the Hadley Center. This is the HAD Crew 4 temperature data, and it's simply the amount per month. So when I'm starting in July and going through June of the next year. And what we can see here is from 1959 up to essentially 1980, there was not a big change in temperature. When we add in the data up until early 2014, you can see the increase was about 0.8 of a degree
centigrade. This is Northern Hemisphere data.
This is all pretty well understood and published in many, many different ways. What I've done here is a little different, is showing it horizontally. Ed Hawkins has shown a spiral graph now where you can see this growing over time, which is a really wonderful way of looking at it. Anyway, there was a major increase in temperature, which really occurred from about 1970 to 1998. Then when Bardhabunga started erupting, the months Bardhabunga was erupting are the black dots. And so for those 6 months, we began to be much warmer than we were before. And by December of last year and February of this year, the peak in temperature had increased almost
0.8 again.
In 18 months related to Bardhabunga.
Temperatures rose as much as they did from 1970 to 1998.
Global temperatures have increased remarkably in the last 2 years.
Bardhabunga appears
to explain why 2016 is the hottest year on record. Now, I want to talk about another effect of volcanoes on climate that is really surprising. And I showed you earlier this map of the annual mean total column ozone measured at Arosa, Switzerland. And what you notice in looking at this is there are peaks and there are sudden troughs. And from year to year, it's going up and down. I put in here some of the major volcanic eruptions in red. And you'll notice that in many cases, there's a peak up. Sometimes it's not so big, other times it's huge, and then there's a drop down. So in Pinatubo's case, we had a major increase the year of the eruption and a sudden decrease the next 2 years of almost twice as much as the increase. So it turns out if you look at a time-lapse photography, this is now the ozone measured in the northern hemisphere. And every frame is 1 day, starting in February 15th of 2010. And what you'll notice is by the arrow, see suddenly there's a whole lot of ozone coming out right above Iceland. And what's really fascinating is that this was at a time when magma at depth and gases seem to be beginning to escape to the surface. So the red band over here is the time that we're looking at here, extended a little more. And we can see from the tilt data in red, green, and blue that suddenly the ground was beginning to expand. We can see from the earthquake data, these are small earthquakes shaded gray and the bigger earthquakes black, that this was a time when Simonson and others say that the sill at a depth of about 2.5 to 3.7 kilometers down was beginning to break to the surface. Now it's not clear whether this ozone comes from the magma, which doesn't seem right petrologically, or whether it's coming from really hot gases that are coming up through the water table and leading to it. But oxygen is one of those molecules that comes apart a lot easier than some other things. And I don't know. It also is possible that the sulfur dioxide is confusing the satellites, but the guys that control these satellites have worked on that a lot, and they think they can tell the difference. Certainly sulfur dioxide would be expected to come up, but they think this is ozone. So I don't know what the explanation for this is. I have a whole web page that describes the problems here. But this is pretty exciting because what it means is in the future, if we've got a volcano like Eyjafjallajökull, which is looking like it's going to be active, if we see the ozone coming out, we know we've got a couple of months or less than a couple of months before the eruption might happen. We saw the same thing before Pinatubo. A couple of months before Pinatubo, there was this spurt of ozone. In that case, it was north of Pinatubo because that's where the circulation is in the northern hemisphere. But it was due north of Pinatubo, and the timing was exactly right for what was going on at Pinatubo. So there's a good chance, and as I've shown in the earlier graph from the ozone, that really dangerous volcanoes that are going to explode may appear to give off major ozone at that time. Now I want to talk a little bit about warming that happened from 1970 to 1998. And it was apparently caused by ozone depletion. That from 1945 to 1970 or so, there wasn't much change in temperature. The green line here shows the manufacturing of chlorofluorocarbons, or CFC gases. Now, these became very popular in the 60s as refrigerants, as spray can propellants. Remember, back then we could get almost anything in a spray can. As solvents. And the reason they're popular is they're so inert chemically, they just don't interact with much. But it turns out that in 1974, Molina and Rowland, in a paper that ended up getting them the Nobel Prize, showed that when these CFCs are put up way up in the stratosphere, the ultraviolet C radiation is enough to blow the molecules apart. And one of the things they form is chlorine oxide. And when that's gets lower in the stratosphere, particularly in the presence of polar stratospheric clouds and volcanic aerosols, you can get really expedited ozone depletion. When the Antarctic ozone hole was discovered in 1985, we realized, oh my gosh, we got a problem here. This ozone depletion is worse than we thought. And what's amazing is in 2 years, scientists and politicians agreed on the Montreal Protocol on substances that deplete the ozone layer. And that went into effect in January 1989. So this was an excellent case where scientists and politicians worked well together to make a significant change. And as I'll argue in a minute, actually prevented the world from warming more at this time. So in 1993, this increase in CFCs stopped. In 1995, the increase in ozone depletion stopped. In 1998, the increase in temperature stopped. And from 1998 to 2013 was the well-known global warming hiatus. I have on my website a list of more than 50 papers, all peer-reviewed, trying to figure out what in the world was causing the global warming hiatus. It's very interesting reading, but there's no consensus as to what's going on. I'm arguing here that the warming stopped because we decreased the emission, the manufacturing of chlorofluorocarbons. Now, another thing that's interesting here is we can see that there just wasn't much change in temperature from 1945 to 1975. Temperatures increased to 1998. There wasn't much change in temperature until 2013. And then there's been this very rapid change in temperature, which I attribute to Barthabunga. It's very difficult for greenhouse gases to explain these points of inflection, these changes, these sudden changes in trend. CO2 has been emitted at an ever-increasing rate during this whole period of time. So what's going on here? What's the atmospheric chemistry going on here? In normal times, ultraviolet C, which is the highest radiation from the sun that reaches the upper part of our atmosphere, the most energetic radiation from the sun, was keeping the stratosphere, the upper atmosphere warm, the thermosphere. Ultraviolet B was keeping the ozone layer warm, and ultraviolet A was reaching Earth along with visible light, keeping Earth warm. When we have effusive volcanic eruptions, the chlorine and bromine from the volcanoes somehow seems to get up and cause depletion of the ozone layer. We observe the depletion, and ultraviolet B, therefore, is absorbed less. So more ultraviolet B reaches the Earth, the ozone layer gets cooler, Earth gets warmer. We can measure these energy flows. The data are there to support that's exactly what's happening. When you have an explosive eruption like Mount Pinatubo, the chlorine and bromine do deplete the ozone layer, and it works especially efficiently on the aerosols that are just beginning to form at that time. But then the sulfur dioxide mixes with water, making a sulfuric acid aerosol that over time grows big enough to reflect sunlight, primarily the highest frequency sunlight because of the physics of reflection, which is mainly ultraviolet B and ultraviolet A. And this leads to a cooling. When you add in the spray cans and the CFCs, it's the same kind of mechanism as the effusive volcanoes. We end up depleting ozone, allowing global warming for a while, and then it has to recover again. In the case of volcanoes, the recovery from ozone depletion is within a decade. In the case of CFCs, these things last forever. And so it's going to be many, many decades before most climate scientists expect the effect of CFCs to wear off. The problem with the climate models gets back to an assumption made in the 1850s by James Clerk Maxwell. Now, James Clerk Maxwell is the god of electromagnetism. He wrote a series of equations during the American Civil War that are still taught today in colleges and have been used to design everything electric and every piece of electronic that you depend on today. Those equations work extremely well in matter. They're still widely used. Natural philosophers and scientists,
However, have been arguing for
2,500 years whether radiation travels through air and space
as waves or as particles, or in modern physics as
wave-particle duality. Just kind of fudge it all together.
But radiation cannot travel through space as waves. Waves are the distortion of matter, the distortion of a medium. Waves propagate
by pushing a piece of matter out of its way and then having it spring back because of the elasticity or the pressure acting on that matter. This was well recognized and argued about in Maxwell's time. And it became known as thought of something, there must be this luminiferous ether. There must be this something in air and space that allows waves to propagate. Dozens of scientists went looking for it. It was a major topic in physics from 1850 to 1900. But in 1887, Michelson and Morley here in Britain showed by a laboratory experiment that luminiferous ether cannot exist. But then we kind of forgot about it. And so still today, even though it was shown over 100 years ago that it couldn't exist, we still tend to think of light traveling as waves. Now, light radiation can also not travel as photons or particles. Now again, I could talk for several hours on this issue, and one of my best friends is one of the top theoretical physicists in the world today, and I've argued with him for years on it, and he just can't bear the thought that photons are not real things. But I've been arguing that photons mathematically are wonderfully useful, and they've led to a lot of interesting physics. But physically, it's not clear that a photon can exist, and some of the best evidence is shown right here. These red lines are the energy absorbed by a molecule of carbon dioxide. So the molecule is, these are the resonant frequencies of the oscillations of the bonds that hold the molecule together. And what this says is that the energy extracted from the radiation field is determined by the structure of the molecule, and it's done at the molecule. Those packets of energy don't originate at the sun and come to the molecule. So again, there's fairly strong evidence, and I'm not going to convince you in a 1-minute summary, but there's strong evidence that it can't be waves and it can't be photons. The interesting thing is you can't see light. You see the effects of light.
You see these wonderful colors in fall foliage. As we look around the world, we see colors. These are the effects of light.
And we turn the lights off, you don't see those colors. Why do we insist on describing light that you can't see in terms of things that you can see? Waves and particles. Yet for 2,500 years, that's what we've been doing. But logically, doesn't it seem that if you can't see it, it's something different? Light travels through air and space as frequency. Now, when I say that to most physicists, they say, what? Thermal energy in radiation travels as frequency of oscillation. The thermal energy that occurs in anything that has temperature is the oscillation of all the bonds that hold the matter together. And this oscillation is very high frequency. It's trillions of cycles per second. That's a million cycles per second. But this is what heat is. And when we look at Planck's law, which tells us what the radiation is from a black body of a given temperature, you can see here that for Earth, what's being radiated is a very broad range of frequencies, several orders of magnitude. For Sun, it's an even broader range of frequencies. And you notice that there's much higher amplitude from a hotter body. So the hotter the body of matter, the broader the range of frequencies, and the higher the amplitude at the higher frequencies. To increase the temperature of matter, you must increase the amplitudes of oscillation at every frequency, especially the highest frequencies, just by Planck's curve. The navy curve here with the arrow pointed to it is the radiation from an incandescent light bulb. And that filament in the middle of that light bulb is at about 3,300 Kelvin. And it's radiating, it's this broad band of spectrum of energy. But notice the light we're after is just a small part of the radiation. This is why incandescent light bulbs are no-no these days. If you had an LED, it can let out just frequencies in the visible range. Whereas incandescent light bulb, all this heat energy is being wasted, and we measure that. I mean, we know how hot those get. So LEDs and fluorescent lights, however, are just letting out emission that is in the immediate range. So this is another example from personal experience that we all can relate to. The frequencies being issued by a black body are a very broad band of frequencies. Now, since you have to increase the amplitude and increase the frequency, it's impossible for Earth to warm itself. The radiation from Earth, no matter how efficiently you reflect that back to Earth, doesn't have high enough amplitude at all the frequencies to warm Earth. This would be the equivalent of a thermodynamic perpetual motion machine. It just doesn't work that way. If things could spontaneously heat up from their own radiation, we know that's just simply not possible. So the radiation from Earth just cannot physically warm Earth. Now CO2 makes up about 0.04% of the gas molecules in the air today. And each of these molecules is only absorbing a limited amount of frequency. These red lines here are the spectral lines of what's actually being absorbed by CO2 molecules in the atmosphere. This is a small amount of number of frequencies compared to this broad range that I said is necessary for temperature. So you've got this very small number of molecules absorbing these very narrow frequency bands, and there just is not enough heat absorbed by greenhouse gases to heat the ocean. It's just not there. Now, I want to talk very briefly about the Planck-Einstein relation. In 1900, Max Planck postulated that for energy and radiation, energy is equal to the Planck constant times the frequency, nu. Einstein in 1905 suggested studying the photoelectric effect that this energy was equal to h nu, was a light quantum. And these are the two postulates that led to modern particle physics. And it's basically, in atmospheric chemistry, we describe the dissociation of oxygen as adding this h nu to the oxygen molecule, and that blows apart two atoms of oxygen. In common wisdom in physics today, that the energy of an atomic oscillator is E equals h nu, and that this would be the energy of a photon. And then we can add photons together to get a lot more heat. But this doesn't make sense. You can't add frequencies together. It makes no physical sense to add frequencies. If we take white light and we spread it through a prism or cause a rainbow, we get a lot of different colors, each have an energy. But if you add those energies together, you get something in the ultraviolet that doesn't exist. Furthermore, frequency is a continuum. It doesn't have a specific quantum until we put a number on it. And if E equals h times frequency, then energy is a continuum. Houston, we've got a problem here. The whole basic fundamental part of modern quantum mechanics is that energy at the atomic level is quantized. Frequency, we don't see it, but frequency is how we see. Over here, these molecules are oscillating at 550 billion cycles per second. They cause resonance of the cones of our eyes. Our eyes turn that into color. We cannot see frequency, but frequency what allows us to hear. Your voice ends up causing resonance in the hair cells and the cochlea of your ear, and your brain turns that into sound. What we perceive as temperature is a broad spectrum of frequencies. So we interact with each other and with the world via frequencies. Currently, climate models calculate energy by integrating across these bandwidths of frequency. But when you realize that energy equals h nu, you can see that the major peaks absorbed by carbon dioxide, the actual energy in those peaks is 48 times less than the energy that comes through the atmosphere when we deplete ozone. 48 times less. Or the energy here is 48 times hotter. So there's a huge amount of energy coming through this little area here, whereas this big area doesn't have a lot of energy. Climate models today say there's more energy here than here. But you and I know when you stand in the sun, you get a lot hotter than when you stand in moonlight. Okay, so thinking in terms of frequency, we can now understand the structure of the atmosphere, and I'll skip this fairly quickly, but it turns out that all the high frequencies above the ozone layer are absorbed high in the atmosphere, and that's what forms the ionosphere, the highest frequencies. That's what forms the stratosphere, which is from the sun, and that's what makes Earth livable for us. And the atmosphere has nothing to do with waves and photons. Okay. So there are some fundamental problems with the physics of greenhouse warming. Are climatologists going to step up to the reality or bury their heads in the sands of consensus? This is a difficult problem. It's not easy, if you've been working all your life, convinced the greenhouse gases are what's doing it, to begin to look at other things. Earth science is leading the way. I hope what I've showed you today is there's a very clear record, a balance driven by plate tectonics between frequent explosive volcanic eruptions that cause cooling and persistent effusive basaltic eruptions that cause warming. And we see this rapid cycling going on throughout the geologic record. And I would argue that Bardabunga is one of these effusive eruptions that explains why this is such a hot year.